these kind of charge density wave correlations of these bosonic molecules really dominate, and most of the time, or most fields, you get a spin density wave state. But still, it's something measurable in experiment because it's as though these little bosonic molecules of two magnons form a one-dimensional ordered lattice. And so just by a scattering experiment, you can actually measure the distance between these bosonic molecules. So that's done here in a nice neutron scattering measurement on lithium copper vanadate. They measure the wave vector of this kind of solid of magnons up at high field. The saturation field is about 15 Tesla. This material in this field orientation. And you can see that it's kind of a linear function of magnetic field, which vanishes at the saturation field. And the reason for that is very simple. It's basically just measuring the distance between magnons. And what's important here is actually the slope, that the slope is half the magnetization. And that half is exactly telling you that the kind of particles making up this magnon solid have a spin too. You can do a lot of other analysis. What's kind of interesting about this approach, really the reason that we started looking at this field theory, apart from just intrinsic theoretical interest, was that we would like to understand how to extend these kinds of ideas to higher dimensions. In 1D, people can really destroy this J1, J2 chain because they can do DMRG on it to very large systems. We calculate everything exactly. In some sense, we don't need analytical theory, although some of us like it. There are interesting experimental systems in 2 or higher dimensions that are also frustrated ferromagnets. Here's a nice example I quite like. It's a material called fulborthite. It has a kind of Kagame lattice structure like this, but in fact, there's a theoretical paper which does ab initio calculations and has worked out that actually you should really think about this as frustrated ferromagnetic chains with some antiferromagnetic coupling between spins between the chains. And so this kind of system has a very simple state that it likes a lot, which is to ferromagnetically order the 1D chain and antiferromagnetically order the spins between them. And you can see that this state has a magnetization of 1/3 of its maximum value on every triangle. 2 up and 1 down, 2 of them cancel. So this is actually a state describing a magnetization plateau. And indeed, this plateau is observed in fulborthite. It's one of the most sharply defined magnetization plateaus in any antiferromagnet. Experimentalists have found some very intriguing phenomena just below the onset of this plateau that they label N, either for new phase or nematic. So they're speculating this might be a spin nematic state. So to really understand it, we need to develop a theory for a 2-dimensional spin nematic. And it turns out that this kind of field theory can be really readily extended. Another interesting application that I just feel like I should mention, we're working on it now, is to think for other systems where there might be naturally forming bound states of magnons. And one class of systems that are really interesting right now are these skyrmion states in non-centrosymmetric or frustrated ferromagnetic systems. And a skyrmion, is a very large. A large skyrmion is kind of a very classical object. But if you imagine a small skyrmion, it is a region in which locally spins are flipped anti-parallel to the predominantly ferromagnetic magnetization. It has to have a semi-classical interpretation as a magnon bound state of many magnons. And so we can wonder if a very quantum skyrmion system might actually exhibit some of these features. I'll stop. Thanks. I used that most of my time. Appreciate your attention.
Questions? Comments? Yes.
Maybe this is a very naive question, but I was wondering if the topological term in the nonlinear sigma model that describes the system at zero field and the finite field does it do anything? Because it seems like we get gap phase with topological term. I mean, sometimes these topological terms can also be destroyed.
Yeah, it can't really in this case. It's a bit different. Yeah, so there's so this. Yeah, so the difference is that so you're thinking of the usual case of a collinear one-dimensional antiferromagnet. Okay. So that has what's called a theta term, okay, which is a well-defined thing for a smooth configuration of the O3 vector order parameter. So it has a good continuum limit, actually. The topological term here actually requires a singular configuration of the order parameter. Okay. Yeah, because it's actually it's an instanton, so in some sense it doesn't have a continuum limit. It's really a property of it affects a disordered phase, but not any smooth configuration.
The other question was, is there any, in this continuum limit theory that you propose for formation of bound states, which is essentially the linear model with magnetic coupling constant, right?
Yeah.
The sonic. What controls the sign of interaction? Is the magnetic field?
So there's a microscopic parameter, which is this V parameter. So yeah, so maybe it wasn't shown here. So this nonlinear sigma model has a dimensionless parameter in it, which is U over K. Okay, so there's really a family of critical points determined that are a function of that ratio. And at some particular value of that ratio, that's this minus a quarter, the sign of this interaction changes.
So that corresponds to a particular point.
So the whole phase diagram drawn there is for a particular value of that ratio. Okay. So as I vary that ratio, the size of the metamagnetic line will grow or shrink, So for any region like this, and the case where the metamagnetism exists, the microscopic interaction is attractive in that Liebler model. The strength of it depends on where the size of that line. Okay. But that's the two particle interaction. There are higher particle interactions and higher derivative interactions that play a role once we get to finite density.
Yes.
I have a specific question concerning this lithium copper vanadium oxide.
Yeah. Yeah.
You know it's anti-ferroic oxide. Yeah. And the ferroelectric phase is associated with this spin density or spin spiral state.
I think it's the vector chiral state, which is ferroelectric.
Yeah. But one idea is that how this ferroelectric polarization comes about is because of spin orbit coupling.
Yes.
Coupling between them. But in your model, I do not see anything like that.
Yes. Yes. Yeah, good question. Okay, so yeah, so now for simplicity here, I'm focusing on the absolute simplest, just purely Heisenberg model. Of course, any realistic model for any real magnetic material has spin orbit effects like Giacomo-Maria interaction or exchange anisotropy. Okay, they're not included here. So it's an interesting question to ask what happens to all this when you include those effects. Okay, this is very material specific because Giacomo-Maria has a lot of different types in which it can occur, and the D vector can be pointed in different directions. It can be staggered or not. So in general, that's very important to the physics up at very close to the saturation field. It becomes completely dominant, and it will affect the detailed nature of something like a spinomatic state or something else. Now, I can't give a general answer to that question. And in the context of lithium copper vanadate, I don't really know exactly what the nature of the. I would expect the DM couplings are the dominant effect rather than exchange anisotropy in that material, but I don't know what they are exactly.
But the question, if you model DM is one, then there are some kind of super spin current. Quite a few ideas. I thought it directly might help to resolve some of this issue.
Maybe it could, but we haven't tried. So yeah, I'd be very curious to hear what I don't know what the state of multi-Croix studies are in rubber banding.
Okay, yeah, that's one.
Just a simple question. What's the current status of the numerics? I mean, 1D you can do a lot, right?
Yeah.
So what's
Yeah.
the current status and the
So most of
what
this
about 2D?
picture is very established from numerics on 1D systems. From
Even like these multipolar?
yeah. On approaching from high field is a very simple thing you can do, which is to actually look at the first instability of the ferromagnetic state. And it's analytically on paper, it's very easy to look at the one magnon instability. Actually, two magnon instability I could still do on paper for the lattice model because that's a two-particle quantum mechanics calculation. Okay, but if I want to look at 3, 4, 5 magnon, that's still actually a very easy problem numerically because it's a very small Hilbert space problem. So that these instability fields to each of the multipolar states are known basically exactly numerically from there's also DMRG calculations that directly and other exact ionization. It's very easy to diagnose these phases because if you look in a finite system, you look at magnetization versus field. It takes discrete steps. Over here, you can see actually the magnetization jumps by steps of 2. Here it jumps by steps of 3. Very nice thing to look for in a numerical study. Down here, this becomes complicated because the boundary becomes very close to zero field. All the length scales become very long. The Q of the state becomes very long. So there's some indications for this metamagnetic transition, and that's why I drew it as stopping at 4 or 5. I don't think it's very clear from the numerics exactly where it stops, but there's indications that it stops. Any more detailed questions than that? Probably not. For example, you can ask, I'm drawing this kind of schematically. What are really the nature of the phase boundaries here connecting the second order and third order multipolar phases, for example? That's an interesting question.
Okay. Yeah, very short. Yeah.
How would this phase diagram change with finite temperature?
It will become very simple at finite temperature because it's a one-dimensional system. There'll be basically no transitions anymore in there.
I mean, just away from zero temperature a little bit. How would this multipolar phases change?
Yeah, so strictly speaking, none of these phases exist as a separate phase. At any non-zero temperature, there are no transitions in this plane. Okay, for a Heisenberg model in one dimension, there just aren't any. Okay, not even the discrete symmetries can be broken. But of course, there'll be all kinds of crossovers that you can study. Real lithium copper vanadate is, of course, only studied at finite temperature, but it's also not strictly one-dimensional. So this is a kind of detailed question you can ask. But for example, if we look at the second order multipolar phase, its basic characteristic is it has a spin gap for spin 1 excitations. Okay. That's something very measurable, and you can see Arrhenius behavior of certain properties because of that. On the other hand, it's actually a gapless region. The spin 2 excitations are gapless, so it would still have a power law specific heat, for example.
Okay, so let's thank Professor Balents again. So we have a coffee break until 11.